Math 287, Cuesta College. I'm Joe Vasta, and we are going to be covering section 10.1b, the Laplace transform shortcuts. So we are going to have shortcuts for these four functions, and then our list will grow. And I'm going to do the derivation of these shortcuts on PowerPoint. Okay, well, here's the derivation for the shortcut for t to the n. N has to be a positive integer for this to work. So let's go see what happens here when you put t to the n into the definition of the Laplace transform. 0 to infinity, e to the negative st t to the n. Okay, so what I would do on this is I'm going to integrate with respect to t using integration by parts. I'm going to have to use integration by parts n times. So you can kind of go through this detail. This is a derivation, and I'm not going to fill in every little detail, but what I get when I do integration by parts is this right here. Okay, it's quite an expression. I would use the tabular method or the staircase method instead of just using what is taught in the Calculus 2 class. You can get that pretty simply. Now what we want to do is put infinity in for t, and we hope to get 0, and we will get 0 if we take s to be greater than 0. If s is greater than 0, then this says like e to the negative 7t, which gets sucked down to the bottom. You have just polynomials on the top, you'll end up getting 0. When I put 0 in for t, I end up getting 1 there, and all those terms except the very last term, and I did put a t to the 0 there, but all the terms 0 out except this last term. So let's see what we end up getting. We end up getting an n factorial e to the 0, s to the n plus 1. And let's simplify that a little more. We have n factorial over s to the n plus 1, which gives us our first shortcut for t to the n. Just like we had a shortcut for t to the n when we take derivatives, we have a shortcut for t to the n when we do a Laplace transform. It's n factorial over s to the n plus 1. This shortcut is totally worth remembering, especially when you hit future technical classes that use the Laplace transform. Let's go ahead and do the shortcut for e to the at. Okay, I plug this into the Laplace transform, and I believe when we did 10.1a, we did something, and the a was a certain number like 2 or whatever it was. So this is going to be very similar. No integration by parts here. I'm going to rewrite that. E raised to the a minus s times t. S and a are just constants. You can do a u substitution or eyeball it. You end up getting that when you take the antiderivative with an a minus s on the bottom. You put infinity in. You would hope that that thing would go to 0, and will only go to 0 when s is greater than a. So you put infinity in, you get 0. You put 0 in for t. You're putting these things in for t. You end up getting 1 on the top and a minus s on the bottom. So we distribute the negative on the bottom. We get 1 over s minus a. There is the rule for e to the at. Let's go ahead and look at the next one. On the Laplace transform of bt, cosine bt, and we kind of did one like this in class, except now we have a b there. And so this is the one where you have to do integration by parts. I wrote this in red. Integration by parts gives you this, and I'm going to kind of go fast through this because you're not going to have to do this in your homework. You put the infinity in, you want s to be greater than 0, so you'll end up getting 0 for that infinite limit. And so I, which is our integral, equals minus negative 1 over s when you put 0 in, and then you have the minus b squared over s squared. And I'm not going to go through all the details of the integration by parts. You can fill in those blanks if you want. I solve for I put all the I terms on the left-hand side, factor them out, divide, and I end up getting the rule for the cosine bt. has an s on the top. S over s squared plus b squared. Now, this one was in your homework for 10.1a. I don't know if you did this or not. I'm going to just run through this really quickly. It's very similar to the cosine dt. The math majors in here might want to file this away if you ever have to do this again. So I'll go through this really quickly. And the Laplace transform of the sine bt doesn't have an s on the top. It has a b on the top. But you have an s squared plus b squared on the bottom. So that kind of goes through some of the derivations, and we're going to go back to the paper. Okay, so we have we finished the derivation of the Laplace transforms for these four functions. Those derivations, I'm going to include that in the PDF that's next to the video on my website. So here it is. This is what they look like. In a normal class, a face-to-face class, you would be memorizing these puppies here. The cosine has the s on the top. The sine, who you would think would have an s on the top, has the b on the top. And we have these that look like that. You also might notice that looking at the denominators of these four, those denominators remind you of the annihilators. D to the n plus 1 annihilates polynomial of degree n. D minus a annihilates this guy. D squared plus b squared annihilates the cosine or the sine. But it's not just 1 over annihilators, because we also have some weird stuff in the numerators. So what you're going to do in 10.1b, it's going to be a lot easier than 10.1a. You are going to be finding the Laplace transforms using shortcuts. So let's go ahead and do a few problems, and we'll be done with 10.1b pretty soon. Okay. Find the Laplace transform. Another way they can word it, they could say find L of f or find f of s. So that is what we're going to do. I'm going to use the f of s notation. I'm taking this from the land of t to the land of s, and I'm using shortcuts. Okay, so we have our shortcut page, and our first one has a sign in it, and so this right here has sine bt. That's what we're going to be using. So instead of doing the integral each time, we are just memorizing these formulas here. Just like you did with derivatives. When you first learned derivatives, you had the definition, which had the difference quotient, but you don't do that anymore when you take a derivative. You just use shortcuts, and that's what we're going to do here. So this 3 is just out front. It's because the Laplace transform is a linear transformation, or it's an integral. The 3 can be just put out front, and then we do the Laplace transform of sine 4t. Well, I just replace those b's with 4's. So I have 4 on the top, and then s squared plus 4 squared. S squared plus 4 squared. Now I want to clean that up a little. So, I mean, I'm pretty much done with this problem. The Laplace transform happens to be 12 on the top and an s squared plus 16 on the bottom. And so that gives us what we are looking for. Let's go ahead and do problem number 2. Problem number 2, we have, we're going to be using this rule right here, the one that says the Laplace transform of t to the n is n factorial over s to the n plus 1. Well, is this guy a polynomial? And the answer is yes, that is a polynomial. That happens to be 5t to the 0 minus, and then we have 2t to the 4th. So we'll rewrite this. Okay, so now let's go ahead and find the Laplace transform of this function. And because it's a linear transformation, we could just say that it's going to be the Laplace transform of this minus the Laplace transform of that. So let's work on this guy right here. We have a 5, which is a constant, and then I'm going to use this rule, t to the n, which is 0 factorial all over s to the 0 plus 1, so s to the 1. Meanwhile, over here we have 2, and then now n is 4, so we have 4 factorial all over s to the 4 plus 1, which is 5. Let's clean this up. Hopefully you remember that 0 factorial, the definition is that is 1. So it's not 0 factorial is not 0, 0 factorial is 1. We have 5 over s minus 4 factorial is 24. So let me just point that out right here. This is so I don't have to write another step. 24 times 2 is 48, so I have 48 on the top, and then s to the 5th on the bottom. And it's hard to believe that this weird abstract math we're doing is going to help us solve differential equations. And it's going to be the preferred choice of solving differential equations for lots of engineers. Let's go ahead and do problem number 3. Problem number 3 looks like this. We have an 8 cosine 5t plus 7e to the negative 3t. So let's go ahead and see what we're going to do here. Here's the Laplace shortcuts. We're going to be using the cosine, and we're going to be using the e to the at. So the cosine, let's just go ahead and jump right into this. F of s is, I have an 8 there, so I'm going to put the 8 right there, and this is cosine 5t, so playing the role of b is 5, so I'm going to write this as s over s squared plus 5 squared. Plus 7 times the Laplace transform of e to the at. Well, in this case, a is negative 3, so we're going to write this as 1 over s, and then we're going to go plus 3. Okay, let's clean up our answer. And our answer is going to say 8s all over s squared plus 25 plus 7 over s plus 3. Now some of you might be wondering, should we get a common denominator? No, just keep it like this. When you solve differential equations using this, you're not going to want to do that some of the time. So this is acceptable, and that gives us the answer to problem 3. Okay, so the rest of this 10.1b is just going to be some FYIs, okay? So for your information, the Laplace transform of 1 over the square root of t. Now you might say, well, let's go ahead and use the factorial formula, and this is t to the negative 1/2, but what's negative 1/2 factorial? And without talking about something called the gamma function, we are going to go ahead and tell you what this thing equals. This thing equals the square root of pi over s. Okay, so that is just for your information. Now, how did we get that? Well, we went to the definition. So included in the PDF, I'm going to include this derivation. It's not written out in PowerPoint. And that will be included in the PDF of these lecture notes. Okay, so I just wanted to give you this because some differential equations books use this a lot, and I don't want you to never see this. But you won't see this on your homework or on the test. Let's go ahead and take a look at some more FYIs. Okay, the Laplace transform of 1 over t and the Laplace transform of e to the t squared. I'm not going to even have these derivations available, but this one right here does not exist. This one right here does not exist. So the reason I'm doing this is to show you that sometimes your Laplace transform, you go to take the Laplace transform of a particular function, it is just not going to exist. Just like when you take the integral of e to the x squared, you can't do anything with that, and then maybe you would have to do power series. Let's go ahead and do our last page of notes here. This is just a theorem, and when you do your homework, you're not going to be coming back to this theorem. This is just for your information, so this is another FYI. If f is piecewise continuous, we talked about that earlier, on an interval from 0 to infinity, and f is of exponential order, we'll come back to that. It just means it's bounded by an exponential function. So if you have a function that is bounded by an exponential function, then L of f, the Laplace transform of that function, exists for some s. So here's the technical definition of exponential order. You don't have to memorize this or even use this. And we'll keep this here for like the math majors and the people who are interested in this. So this concludes 10.1b. And on our next section, we're going to find out how to find the inverse Laplace transform. Have a good day.